Hello everyone, welcome to the next video in this standard level course. Today's question is all about geometric sequence and series, and it's taken from, as you can see, part 1.3 of the syllabus. Nothing too tricky here if you really know your sequences and series, but there's some parts about definitions and so on. This is one of the longer questions. You've got 16 marks here. Should take us about 15 minutes if we're thinking on exam day, but it is perhaps a relatively easy extended response question. So just reading the question, we can see it involves a geometric sequence that's given to us in the question. We don't know exactly what the values of the terms are. We've got them in terms of this variable m. We're probably going to have to find that and then do some other things around that. So let's get stuck in, see how we do. So first off, we're going to want to look at this first section. So it says the first three terms of an infinite geometric sequence are blah. Now, we don't have to worry too much about the infinite part for now. Remembering that the definition of a geometric sequence is one where each term is multiplied by the same ratio, the common ratio r. So the infinite thing will probably come in a little bit later when we start thinking about sums. Remember, you can sum infinite geometric sequences provided the ratio is less than 1. So first off, we're asked to write down an expression for the common ratio r. Again, write down, quite a key word here. We know we shouldn't have to think too much, but it's should be fairly straightforward, should be in our face. So we're just going to write r is, now remember, the common ratio is what I have to multiply each term by. So if you think about the sort of general definition of a geometric sequence, it's that un is r times un minus 1, i.e. r times the previous term. So a little bit of rearranging there tells me that I can write the ratio as the quotient of one term over the previous. So I'm going to write term 2 over term 1, and in this case I'm going to have 6 over m minus 1. So not too tricky to write there. That's what my answer should look like. Next, I'm asked to hence show that m satisfies this equation. Now, obviously I don't have enough information there to really know, because I've got r that I don't know, I've got m that I don't know. So I'm going to need to probably find another way to write r and equate them. So what I could do is also consider that r is the ratio of the third term to the second. So that should be a 3. And again, I can just substitute in now. That's m plus 4 over 6. And then, because these are both r, I can equate them, giving me the equation 6 over m minus 1 is equal to m plus 4 over 6. Now, what this gives us actually is a really nice technique for when we're dealing with geometric sequences with an unknown ratio, or perhaps an unknown variable like m here, is we can use this technique all the time. So it's what we've really done here is we've written u3 over u2 is equal to u2 over u1. And it works especially nice if u2 is a simple term, because we're going to end up squaring that one. But it's a nice little trick when we're doing these sorts of problems. But anyway, we can now rearrange here to say that 36 is equal to m plus 4 times m minus 1. And then we can simply expand the right hand side to come up with 36 is equal to m squared plus 4m minus m minus 4. And we're hoping that when we rearrange this, we get what was given in the question. And it's looking pretty good. So we've got the m squared, 4m's, take away 1 is leaving us with 3m. And then we've got negative 4 already. We bring 36 over for negative 40 equals 0. So looking good so far. That first section, not too tricky. Okay, so we've got m satisfying this equation. Now it's worth noting here with these longer questions, some people do have a feeling that if you can't do the beginning, then you're sort of locked out of the question and you can't do very much else. If you note the way this question is written, regardless of whether we can do this first section or not, we can just jump straight back in here at B, because the last section was a show that question. We're actually given the equation in M. So even if we couldn't work with the geometric sequence to find M, we're given this equation, so we can start again in section B. And that's really the way these questions are designed, so something to be aware of. All right, now find the two possible values of m. Well, what we're going to be looking at here, of course, is solving the quadratic given in the previous section. So let's just refresh our memory. That's m squared plus 3m minus 40. So here we go. We're solving for this equal to 0. Whenever we're asked to solve a quadratic, we kind of have that checklist in our heads that we want to go through. First, we'll see if it factorizes. If it doesn't, we can then think about something like completing the square, if you want to do it that way. And then, of course, we have the fallback formula that is always going to work for us. This one seems fairly straightforward. I'm looking at the factors of 40, not quite a few, but I'm thinking 8 and 5 differ by 3, so that's probably going to be what we're after. So m and m, 8 and 5, one needs to be positive, one needs to be negative, so that I get negative 40. So I'm going to go with positive 8, negative 5, and I think that's going to give me my solution. So I get two possible answers here. M is negative 8 or 5. So two possible answers for m, and you would find that if you substitute either of them back into the initial terms, then it will form a geometric sequence. So that's part 1 done. Lovely. Part 2 says find the possible values of r. Remember, r is the common ratio in this problem, and we're given values, so that plural. We know we're looking for more than one. So we go back to our previous section, looking for our expression here in terms of r, and we can see it's 6 over m minus 1. So all we need to do is substitute into that expression for each of the different values of m. So this gives us 6 over negative 8 minus 1, which is 6 over negative 9, or negative 2/3. Or we have 6 over 5 minus 1, which is 6 over 4, or 3 over 2. And there are two possible answers for r. Okay, not too bad at all so far. Which brings us on to the third section here, where we're told that the sequence has a finite sum. Now, of course, we're harking back to the original problem, which told us it's an infinite geometric sequence. For it to have a finite sum, we need successive terms to be shrinking as they go. If you think about a sequence where that doesn't happen, something like 2, 4, 8, 16 here, obviously each term is getting larger and larger. If we were to add those, our total is getting even larger, and it's what we call unbound. This is just going to shoot off to infinity. So no sensible finite sum here. What we need is for our terms to be shrinking as we go. So that essentially is the condition that the ratio, the common ratio, is less than 1. Now, we put an absolute value symbol around this condition because we're okay with it being negative. We would get an oscillating sequence where we vary between positive and negative. But again, so long as the terms are shrinking in size, we can add them and get a finite sum. So that's our condition here, and you can see it. I've copied and pasted the formula booklet across here. We've got section 1.3, which is about geometric sequences in general, and then section 1.8 brings in the sum of an infinite. These two formulae are actually kind of the same if you substitute in the smaller than 1r value, and then of course r to the infinity would become 0. But they give you explicitly that second formula, and it's handy to use. And there, of course, is the condition we've just discussed. So we need to have that ratio strictly less than 1, so that terms are decreasing as we go, and we can get a finite sum. So that's the condition that they've asked for. State which value of r. Well, we were given 2 on our previous answer. We had negative 2/3 and 3/2. Here they are. You can see them. So one of those is the right one. Well, obviously 3/2 is 1.5, so it's not going to be that one. So we need r as negative 2/3, and we're asked to justify your answer. So we're just going to write something like, since absolute value of r needs to be less than 1 for a finite sum. They just want some reason, some indication of you knowing why you've chosen that ratio. And it's of course because that's the one whose absolute value is less than 1. All right, and finally calculate the sum of the sequence. Again, we're given the formula. This shouldn't be too tricky. Like I said, just be aware that these two sections are actually separated in the formula booklet. This one sort of occurs down the page a little bit. but they are very much related to the same thing. So the sum, perhaps I should, write sum to infinity of our geometric sequence is the first term over r minus 1. So it's actually a pretty simple formula. So let's go back and figure out what our first term was. We were given this is m minus 1. Now here's the tricky part, I suppose. You've got to make sure you're using the right m. To generate our negative 2/3, we used an m value of negative 8. So our first term, if we put negative 8 in here, is going to be negative 9. So that one goes in there. Just a little twist in the tail there. Make sure you're using the right m value. And then we are dividing that by r minus 1. Well, negative 2/3, take away 1 is going to lead us to negative 5/3. The negatives cancel, and we get 27 over 5. You can even simplify that if you like to 5 2/5. But there we go. That is the finite sum of our infinite geometric sequence. Remember, that is only possible when that r value is less than 1. And there we go. Thanks very much for watching.